This is a radical. Now, I know you may have heard of it as a square root, and in this case, it does represent a square root, but the actual symbol itself is called a radical. Now, a radical is just a shorthand for what's called a rational exponent. Now, when I say rational, I don't mean rational like thinking clearly or being logical. I mean ratios. So a rational number is basically a fraction. Any number that can be expressed as a ratio of two whole numbers is a rational number. So like 4 is rational, 1/2 is rational, 15 over 27 is rational, 1/3 is rational. The square root of 2 is not rational. Pi is not rational. You cannot make a fraction out of two whole numbers that will give you either of those. Okay, so if I have some number underneath some level of root, that is the same thing as that same base to the reciprocal of the root. It's really that simple. This is less of a rule and more of a definition. A root is equivalent to a reciprocal exponent. So as you can see, I've got the root and its reciprocal. So let's take a look at a couple of examples, and we're actually going to come back to this definition. So if you just wrote that definition in your notes, leave some space around it because we are going to update it in a moment. But let's do some examples first. The cube root of 5, nice and easy. Well, that's equivalent to 5 to the reciprocal of this root. So we could call that 5 to the 1/3. Example 2. Square root of x. Now, you'll notice that we don't have a number in the radical there. Mathematicians don't want to make any numbers that they don't have to. You'll also notice that we don't write the 1 in front of the x. We don't write the x to the first power, right? These are things that we just skip because they're assumed. The most common root you'll see is the square root. So if there's nothing there, you can assume it's a 2. So this is x to the 1/2 power. Now what if you have something like, let's say 4 to the 3rd power? And we've got the square root of that. Well, it still works out the same way, yes? It would be 4 to the 3rd power, except instead of square root, we're going to put to the 1/2 power. And we already have a rule for this. That was a couple of videos ago. When you have a base with an exponent raised to another exponent, you multiply the two exponents together. So this becomes 4 to the 3/2. Notice how the 3 ended up on the top and the implied 2 ends up on the bottom. We're going to do one more example like that, but I think we can update our definition pretty quick here. Example 4. Let's say we've got the cube root of n to the 6th. Well, again, that would be n to the 6th to the 1/3 power, right? The cube root is the same thing as 1/3 power. Well, that gives us n to the 6/1 times 1/3, n to the 6/3, which is n squared as our answer. Again, don't be afraid of fractions. Multiplying fractions just means multiply straight across the top and straight across the bottom. And 6 divided by 3, well, hopefully you can do that without a calculator. So it's looking to me like our definition could use some updating. If we have the nth root of a to some exponent m, that equals a to the m over n. And that's the one that should go into your notes. So we're going to do a couple more of these, and we're going to pick it up a little bit. So what if I have the fourth root of x to the third y z to the eighth? Again, don't be afraid. It seems like this is a big complicated problem, but it's not. We're just going to break it up into smaller subproblems. Let's just look at the x to the third. The fourth root of x to the third is x to the 3/4. Right? The exponent goes on top, the root goes on the bottom. How about the y's? Well, that's actually y to the 1 power. So the fourth root of y to the 1 power would be y to the 1/4. Right? 1 divided by 4 is just 1/4. This is why fractions are convenient, because it's just a shorthand for division. And then how about z? We've got z to the 8th, and then 4 on the bottom, so that would be z to the 8/4. Well, wait a second, I know what 8/4 is. 8 divided by 4 is 2. Now, I don't know about you, but once I learned about fraction exponents, I more or less gave up on radicals altogether. Radicals always confused me. They made it very difficult for me to figure out what steps to do things in. It made it tough for me to see what was actually going on. I was always much more comfortable with fraction exponents because I took a lot of time to get comfortable with both the rules of exponents and the rules of fractions. And that's sort of my final note here. When using fractional exponents, note, all of the rules you know about fractions and exponents still apply, right? The fact that we have put fractions in our exponents doesn't make fractions behave any differently, and it doesn't make exponents behave any differently. So these rules, these 5, 6 rules that we have put up, they apply to all exponents, including ones with fractions. So you're not really learning anything hugely new. You should already know how to handle fractions, and if you don't, I suggest practicing. And you definitely should be able to handle exponents after all of these videos.